In this screencast, we're going to look at the various means we have to manipulate the data in the Redshift key value store and look at some of the common design patterns that utilize these features. In our earlier screencasts, we've seen that Redshift implements computation nodes linked together by a key value store. So far, we've had store schemas which were just a single string, and our nodes have just requested the store content unmodified. However, Redshift gives us much more powerful ways to structure and manipulate our data flows. Firstly, a store can have a more complex key schema than a simple string. Keys can be composed of a hierarchy of elements separated by forward slashes. There can be up to 7 elements in a key schema, so for example you might have a schema of string, 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 which represents year, month and day. Stores can also have various properties imposed upon them. For example, a store can have a time to live property which limits the lifetime of a given value in the store. Similarly, node inputs have a rich set of properties that allow us to filter and combine store data in a variety of ways. The select property is analogous to an SQL where clause. It specifies a subset of the store that will trigger the node. Subsets can be a simple key, such as bucket dogs key rover, which means only data about rover will trigger the node, or it can be a wildcard of which there are 2 variants. In this first variant, we'd select all dogs with a key of terriers and process them individually. If we add an asterisk to the select, we will again trigger the node on each terrier that is added, but we will be passed an array of all terriers on each invocation of the node. A node input can also specify additional data sources to be added to the data passed to the node. There are 2 different ways of specifying this, lookup and with. Lookup simply specifies 1 or more additional buckets to select data from. So in our dog example, I might look up the accessories bucket and select the dog toys key, so I'd have details about both Rover and any toys he might want to play with. With works similarly to an SQL join, in that it allows me to select data from the second source which matches a key in my first source. With is most commonly used with anchors. Anchors are specified by putting a $sign and a string in the key selection of the first source. They may then be referenced in the with clause. So in this example, I'd join dogs to their licenses and get the details of a dog and his license in one hit. That's an extremely fast summary of the facilities for managing and manipulating data in stores with Redshift. To get a fuller and more detailed view of this, I suggest you go and look at the nodes and stores sections in the Redshift documentation site. So much for the ways we can specify keys and the operations on them. There is much richness here, but it may not be immediately obvious how they may be combined to make useful processing patterns. So we'll look at 4 common use cases: sliding time windows, deduping data, caching, and reducing. In streaming data processing, fairly evidently, data can grow without end. However, many applications have a window of time over which data is actually relevant, say my last 2 weeks of emails or the last day's worth of temperature readings. Using the time to live attribute of stores can ensure that a SIFT only has to deal with these limited data sets. It's worth remembering that the time to live attribute can be attached to a store in general or can be explicit for the output from a specific node. It's not uncommon that data coming into a SIFT may be repeated more than once, for instance, retried emails, but that there is a requirement that the SIFT enforce once-only programming semantics. This can be achieved by joining 2 stores, one with the stream of incoming data and another that records the fact that a given chunk of data has been already processed. You can use the with operation to achieve this. Frequently, a stream of data will require additional data to be processed, which may come from external systems via, say, an HTTP request. In this case, using lookup on a stream with a TTL will ensure that the external data is not requested on every node invocation, but just refreshed on a regular basis. Another regular pattern is that a SIFT will generate many small computation results that need to be aggregated regularly to provide a summary. That might be things like percentage of spam mail per week or average fuel consumption. Using select with the asterisk wildcard will give the node an array of all matching records to iterate through. In order to make these patterns a little more concrete, I've prepared a somewhat whimsical sift which continues to use our dog analogy. You'll find the code for this example on the Red Sift GitHub repository at Sift Patterns. In this example, we have dogs coming to a kennel to be fed. Dogs should only be fed once a day, and when they are, an account should be kept of the number of meals that they've had so they can be billed, and the larder should be depleted of tins of dog food so we know how much we got left. Now let's look at our DAG visualization side by side with the sift.json file. The delivery van comes once a week and stocks up the larder with dog food. The kennel emits visits from random dogs every 5 minutes. The dog visit outputs have a time to live of 1 day. The dog feeder node takes in dog visits and joins them with the fed store. If there is no entry in the fed store for a dog visit, then the dog has not visited yet that day and the dog can be fed. The dog feeder node will emit a fed message to ensure that the next time the dog visits it will not be fed, and it also emits a meal message so the accounts package can track the billing. The dog feeder node also decrements the dog food level in the larder each time it feeds a dog. The dog feeder node outputs meals with a key schema of a timestamp and the name of the dog. And once a week, the daily accounts node runs and aggregates the list of all the meals, counting up meals for each dog and emitting a bill for each dog, which is the total of number of meals it's had. That's it for now. Thanks for watching.